Okay, now we're back for question number 4. I know I'm rushing through this a little bit, but I want to get these videos up as fast as possible so that you have something to look at before your exams, which from when this video was made is tomorrow. So let's take a look at question number 4. I'll fold this and get it into the frame. You may or may not have heard my wife sneezing in the background. The question below provides the formulas. In the question below, provide the formulas and explain your reasoning. A wireless transmission system has bit error rate p bits per second, where p is a probability vector, or as I guess a constrained probability vector, because 0 is less than p is less than 1. So p is neither less than, so it's not actually a probability, but it's on a subset of probabilities. So I can treat it like a probability. Let's see, and a packet length of n bits. Okay, so my length is equal to n, and then it says what's the probability that a packet has an error. Okay, so let's look at this from the perspective of receiving a packet in this network, this hypothetical network, and what it would mean to receive that packet, how I would receive it, and what kind of process that is, right? So I am my receiver, and now I draw slots for where my packet bits are coming in. Alright, so these are, let's pretend these are bits in the buffer. So I see the first packet, or the first bit come in. It has a probability of being an error of p. So let's say this is not an error. So I'll say that p is equal to p, right? That's our p. And I'll say that q is equal to 1 minus p. So the first bit comes in, no error. That's q. This next bit comes in, no error. That's q. The next bit comes in, that's an error. That's p. This is q. This is q. P. Q. P. Each one of these is an experiment, right? Each and one, like every single one of these bits that comes in is an independent experiment. So essentially I can treat this like a Bernoulli distribution. Bernoulli distribution. My brain is fried, it's too early. It's definitely a Bernoulli distribution, right? So essentially each one of these is an experiment. Each experiment has the same likelihood of producing the same outcome. They're all equiprobable experiments. So they distribute as a series of Bernoulli trials. So I now choose something, right, because I have n bits, right, and I'm choosing however many are going to be an error that I want to look at, like how many of these experiments resulted with an error. And we say, what is the probability that a packet has an error? So we're looking for exactly one error. Okay. So how many of these experiments resulted with a packet generating one error? So each bit being an experiment. So okay, I generate that error with a probability p. I have one such p. And I have no error with a probability 1 minus p, n minus 1, right? Why n minus 1? Why does it distribute this way? Well, let's take a look again at another experiment. This time with only 4 bits. So I have exactly one bit in error. So I'll say this bit is an error. This bit is not, and this bit is not. Okay. I have 4 choose 1 ways of putting this p into this experiment, right? I can put it in that position, I can put it in this position, I can put it in this position or that position. So I have exactly 4 choose 1 ways of placing this error, and that's where my choosing comes from. I have the probability, because if I look at the probability of this outcome, if I say the probability of this outcome, it's equal to q times q times q times p, right? That's the probability of this. Now, if I look at another experiment, and this is uglier because I'm rushing so that you can get this video sooner, and I put the p over here at the first position, okay, q and q, the probability of that happening is P times Q times Q times Q. So you can see these two probabilities, these are the same, right? And that's really where your choosing comes in. I can put this anywhere in any order, right? And I always get the same probability out. That's this probability here, right? So I have n choose 1 ways of getting that probability. If I were to condense this, like simplify this, I would have Q cubed and P to the 1. Well, I have 4 spots, so this is 4 minus 1. And the same is true here. So that's why it's a Bernoulli distributed, or why we can see it as Bernoulli trials. So that's how we get our probability of exactly 1. P of x equals exactly 1. Okay, so now we say what is the maximum possible packet length so that the probability of a packet has an error is at most epsilon. At most. So at most means less than or equal to epsilon. So part 1 is on the left. Part 2, we add this epsilon. Epsilon is a tolerance, right? So if I think about epsilon, again, it exists as a way to constrain this problem, right? So how do we get a little bit less of an error, right? Let's say epsilon is much, much less than 1, right? So we're constraining our probability space. Now what we have here is how do we change n such that this statement is true? And we don't actually have to change n, we just have to find the formula for it. So that's the solution to question 4, part 2. Part 1 is the P of x equals 1 is that. Part 2 is that whole entire statement such that it is less than or equal to epsilon. So I'll see you again in the next video for question 5.